In this video we're looking at the expectation and the variance for the binomial distribution. So we'll look first of all at a binomial distribution where n is 12 and p is a third. So that is, we're doing something 12 times in a row and the probability of success is a third. Now, how many times would you expect to be successful? If you're doing something 12 times and on each individual attempt the probability of being successful is 1/3, just think of it logically. How many times would you expect to be successful? And you're probably thinking, well, a third of 12, which is 4, and that's exactly right. So if x follows the binomial distribution, to find out the expected value of x, the mean, the expected number of successes, you times your n and your p value together. And that's something that you need to learn. The proof of that we needn't worry about, is outside the scope of the knowledge you need for the exam. There's a reference there where you can find a bit more about it in the textbook, should you want to. And with the binomial distribution, just as there's a formula for the expectation of x, there's a formula for the variance of x as well. Not one that you could just come up with on your own, and one I'm just going to give you and tell you what it is. If you want to find out where it comes from, again, you can look back in your book, in the textbook, and it is there, but you don't have to understand where it comes from. So the variance of the binomial distribution is n times by p times by 1 minus p. And as some textbooks, instead of using 1 minus p, use q to represent 1 minus p, you may also see the notation npq being used instead. So if we try to use these formulae on an example, well, if we look at the one we had earlier, well, it's actually slightly different to the one we had earlier. I've changed the value of p here to be 0.25. We're going to first of all find the mean and then the variance of this distribution, and then in the second part of the question we're going to find out a probability, and we'll look a bit more at that bit in a minute and see what that means. But first of all, the expected value of x, because that's what the mean is. If you're asked to find the mean, it's the expected value of x. You can use these terms now interchangeably. The expected value of x, and I've used this symbol here mu, the Greek letter mu, to represent the mean. Something else that you can do, and it's common notation. For the binomial distribution, we can just say it's n times by p. So that is a 12 times by 0.25. A quarter of 12, that's 3. If you actually bothered to work out all the probabilities here, the probability that x was 0, x was 1, x was 2, x was 3, all the way up to 12, and drew out a probability distribution table, like we did earlier in video 2, and used the old formula, which was timesing each probability times the x value, you would get exactly the same answer. But it's just the formula we have here, the NP formula, only works with the binomial distribution, but it's a much, much quicker way of getting there. So for the variance, and again the notation I've used here is sigma squared for variance. That's the Greek letter lowercase s, so sigma squared. It's npq or np 1 minus p, whichever notation you want to use. So it's 12 times by 0.25 times by 1 minus 0.25. If you times those together, you get 2.25. The variance in itself doesn't really mean very much. It's only if you were comparing two different distributions and you were comparing the variance, then the one with the smaller variance has less variability in its outcomes. The one with the bigger variance has greater variability with its outcomes. I do accept that if you just work out the variance of a distribution and have nothing to compare it to, it is to a certain extent a meaningless number unless you do it in comparison with something else. Now let's look at that second blue bullet point, finding a probability. It says find the probability that x lies between mu minus sigma and mu plus sigma. Well, mu is the mean, so mu here is going to be 3. And sigma, well, it's a square root of sigma squared. It's a square root of the variance, so that sigma is the standard deviation. And that will be the square root of the 2.25, which is 1.5. So, just having a new slide to work with, we've just said that mu was 3, we worked that out, and sigma is 1.25, and I want to work out the probability that x lies between 3 take away 1.5 and 3 plus 1.5. That's just by substituting in the 3 for mu and the 1.5 for sigma. So 3 take away 1.5 is 1.5, 3 plus 1.5 is 4.5. So we want the probability that x is between 1.5 and 4.5. Now we're dealing here with a binomial distribution, the number of successes we get. So we can only have whole number values. You can't have 1.5 successes, you can't have 4.5 successes. So if the number of successes has to be bigger than 1.5 and smaller than 4.5, it can actually be 2, 3 or 4. So we can change it into the notation we've got here, that it's between 2, but it is either 2, 3 or 4. We either have to work out the probability it's 2, the probability it's 3, the probability it's 4, and add them together, or to speed things up we can use the tables. And if you need the probability it's 2, 3 or 4, then if you use the tables you need to rewrite it as less than or equal to probabilities, because our stats tables are less than or equal to tables. So 2, 3 or 4 is the same as less than or equal to 4, which is 0, 1, 2, 3 or 4. And if I say 0, 1, 2, 3 or 4, the things I don't want there are the 0 and the 1. So that's why I'm going to take away the probability that x is less than or equal to 1, which is 0 and 1. So if I have 0, 1, 2, 3, 4, take away 0, 1, I'm left with 2, 3, 4, which is what I want. So in your probability tables, if you turn to the binomial probability section, you're looking for n is 12, that table. Work your way along to the column where p is 0.5. When p is 4, when the 4 value is over on the left, you should get a probability of 0.8424. When 1 is over on the left, you should get a probability of 0.1584, and if you do the taking away, you'll get your final answer here, which is 0.6840. So that's how you can use the formula for mean and variance for the binomial. In the next video, we'll see how we can use some of this with the geometric distribution.